this session is entitled Epidemiology and Basis for Current Radiation Protection Standards. And I'm going to be relatively brief in introducing this. I already related that I had the very good fortune to have Mr. Herbert M. Parker as a mentor, if you will. And he used the phrase, epidemiological studies are studies of human misfortune. And I think that is a very apt statement. And I think along with that, we have a responsibility, a special responsibility, to those individuals who are participants in those studies to do very careful and detailed studies, as we've already heard examples of, and then use that knowledge to the maximum extent possible. So the way I'm going to run this panel is we have two individuals who have not spoken before, and I'm going to just ask them to come to the podium. First, Richard Bull, and I'm going to let him say just a few words of introduction and then proceed into his presentation. So pleasure to have you here, and we look forward to your remarks.
Right, thank you very much. Good afternoon. My name's Richard Bull, as you can probably tell by now. I've been working on the Harwell site now for about 30 odd years doing internal dosimetry. And I've probably gone stir crazy after that amount of time. I'm going to talk very, very briefly about internal dosimetry in general as a kind of supplementary to the very good talk that Bruce gave a few minutes ago. So I've only got 3 minutes, so I better crack on pretty quickly. Internal dosimetry is due to internal contamination that's been taken into the body by either ingestion, injection, absorption across the intact skin, or inhalation. Generally speaking, inhalation is by far the most important route of intake for occupational cases, and I think that's certainly true with the MIAC cohort. Unlike external dosimetry, once you've got active material in the body, then you go on receiving dose for a long time after you get removed from the exposure to activity. And also, it cannot be measured directly. You have to use indirect methods in order to get some idea of the internal dose. Okay, so that reiterates most of the points I've already made. We've got to use indirect methods. The other point is that external dose is often dominated by low LET radiation, whereas internal dose is predominantly high LET, particularly in the case of MIAC. We essentially have three detection strategies for internal dosimetry. You can measure activity before it gets into the body, and that's air sampling. You can measure the activity when it's in the body, which is in vivo monitoring or autopsy, or you can measure it when it leaves the body, and that's excretion sampling. Autopsy, of course, wouldn't be a very practical means of doing normal regulatory internal dosimetry. Even in the UK, we don't expect people to fall on their swords just for the benefit of the dosimetry department. This is a personal air sampler. Many of you will be familiar with it, but some perhaps not. You have a little sampling head which you wear close to the breathing zone. You draw activity onto a paper by means of a little pump that you wear on a portable pump you wear on your battery-operated pump you wear on your belt. And you take the filter off at the end of the exposure period. You account it under a detector, and you get an idea of what the inhaled activity might have been. It's a simple, quick, and direct method, but its disadvantage, of course, is that you're never quite sure how representative it is of the inhaled activity. And then in vivo monitoring, this is my boss pretending to be the internal dose, the in vivo monitoring guy. You basically stick the person under an array of detectors. You measure the radiation coming off them. It's fine for gamma emitters. You can also, with care, use it for americium, either in lung or in the case when it's got taken up systemically, you can stick a detector by the kneecap or wherever the bone happens to be close to the surface. And But I should, of course, say that it's not much good for for measurement of plutonium contamination unless you've got a very good handle on the ratio between americium-241 and plutonium. And then finally, we've got urine and fecal sampling, and I think probably this is fairly self-explanatory. Workers give regular urine samples or perhaps fecal sampling. At MIAC, there is urine data, but in the early days in particular, it's rather sparse and a very, very high limit of detection. In fact, when I first had a look at a paper about MIAC urine sampling, I thought they'd got the units wrong, but they hadn't. If you've got insoluble material, then fecal sampling starts to become the more sensitive means of detection, whereas if you've got stuff that's moderately soluble, then you're better off with urine sampling. Okay, so interpretation of these results is important. We need to relate what comes out or what gets retained in the body with what went in the first place. That's to say the intake, and we've got to convert that intake into dose. So we need various types of models in order to do this. We need biokinetic models in order to tell us how much is in any given organ at any given time after intake. And we need dosimetric models to relate what's in the source organ to what dose gets delivered to the target organs. So this is just what a typical compartmental model is going to look like, and this is the you have material getting taken into the transfer compartment, essentially the blood, and then transferred to other organs. And how it gets into the transfer compartment depends on the intake route. And we've also got the lung model is displayed there. You see the physiological model, and that's used to construct a compartmental model, which we use for the dosimetry. Okay, so in the old days, when internal dosimetrists used to produce point estimates of intake and dose, and if anybody asked them for uncertainties in their dose estimates, they changed the subject and walked away. But nowadays, that's not good enough. We're supposed to produce uncertainties on these doses for the benefit of the epidemiologists. There are large uncertainties in measured quantities and in model parameter values. And so we have to assign prior probability distributions to these quantities. And then we use typically Bayesian methods like Welmos or Markov chain Monte Carlo to produce posterior distributions of intake and dose. And in that way, we provide data for the epidemiologists in the form of calendar year organ doses with uncertainties. And then it's up to them to convert that into risks. So that's a very brief run through internal dosimetry. I've only been involved with this project, now, the MIAC project, for barely a year now, and it's certainly a very interesting one. My main interest is the fact that the main source of really good data is in the autopsy, whereas obviously that's not something we've had much experience with in regular dosimetry. So thank you very much. That's the brief description over.
Great. Well, thank you very much. I might take time for one or two clarifying questions, if there are any. One.
Yeah. Hopefully this thing works. Can you hear me? No. So basically my question is just, you said that the interesting data is in the autopsies. Have you ever been able to compare data that you took in vivo to an autopsy later through some unfortunate set of circumstances?
Yes, I can speak to that.
Okay.
There's in MIAC.
Push the button. Dude, you.
In MIAC, there's about.
No, it's still not on.
There, it's on now. Okay, there are about 500 people that have urinalysis and autopsy data. In the past, the comparisons did not look too good. I think with the new dosimetry, we're probably going to revisit that. This is a dosimetry problem, not for statisticians like me, but still there is some, and we have looked at it statistically in the past, but
Okay.
it raises a lot of questions.
And the results have been sketchy?
It's just challenging. I mean, it's a lot harder to go from urinalysis to a dose than it is to go from, we're looking at the dose derived from both, and there's a lot of clear uncertainty there.
Thanks.
Yeah, I might, while the next speaker's coming to the microphone, ask if anyone from the USTUR wants to offer a comment on this issue that was just raised. So go ahead, Dave. You can offer your comment. Wow.
Yeah, just a question about the biokinetic models and just how good do you think they are? I mean, have they really been validated?
Well, they're based on a fair amount of data from volunteer studies, from animal studies, and so on. And I think they've certainly improved a great deal since I first got involved in internal dosimetry, where we had the very simple ICRP30 models. I would say now that they're reaching a reasonable degree of sophistication, but I think there's always room for improvement.
Yeah, sophistication isn't the same thing as realistic, of course.
One of the things that we did do in the radiation protection dosimetry journal article series, we have one article on comparisons of our predictions with the measurements with predictions using the Leggett model for the systemic plutonium, and actually they came out very well.
I would just add to this in terms of our laboratory at Lovelace in New Mexico did huge amounts of work in terms of biokinetic models, in terms of animals, and our ultimate goal was not only to accurately estimate the dose to those tissues of those animals, but also provide a basis for the humans. I would say, in my overall experience, the work in this area of these biokinetic models has been extraordinarily successful, and I would give them a high degree of scientific validity as a personal, professional view. Let's hear from, introduce yourself and...
Hello, my name is Maya Aftanilashvili. I am from U.S. Transuranium and Uranium Registries, the research program that was designed to follow up the nuclear workers who decided to donate their bodies or parts of the bodies for the science, exactly to test and validate biokinetic models. That's what we do. So we measure the activities, plutonium, americium, uranium in the tissues post-mortem, and what we call autopsy data, and we compare to the predictions of the model using the urine measurements. And in most of the case, then what we do the reconstruction of the case, or individual cases, using simultaneously feeding the urine data and the autopsy data. And that always requires some optimization of the model to get the best estimate of the intake and the dose. But with the urine measurements, yeah, we have significant uncertainties, of course. But autopsy data, they give us the final answer we can compare and verify how well the model works.
There are a number of papers from that group. I'm proud of the fact that under such other duties as assigned in 1966, I organized the meeting that gave rise to the U.S. Transuranium Registry, and I'm proud of the fact my father is in it, and I convinced him not to give his whole body. My mother was a little bit reticent on that, but he gave a partial body donation, and my first introduction to the world of bioassay was when I asked my father, when he first started working in separations at Hanford, what's that gray box on the porch? Seems to come every now and then. He said, that's the pee bottles. I got to collect my pee at home to match up with the pee at work, and they're going to use that to determine if I've been exposed. I didn't ask you exposed to what. Later I did. So let's go ahead and proceed then to our next speaker, Dr. Homolka, and I'm going to let him say a few words of introduction, and then I think he has 7 or 8 slides.
Okay, thank you for introduction and good afternoon. My name is Hamaoka from Tokyo, and it is really honor to be included as a panelist because I am really new to this field. Actually, I'm teaching marketing research in Keio University. And since Fukushima disaster, we Japanese are concerned about health risk of radiation. And someone says exposure under 100 millisievert is no problem. And other says the risk is linearly increases, so we are really confusing. But so I began to try to understand what kind of analysis is conducted in this field, and I critically examined literature on the airborne survivor and the nuclear worker data, and I identified some limitations in major radiation epidemiological studies. Due to time limitation, I would like to introduce two limitations today. The first one is incomplete model selection, and the second one is aggregation of individual level data that leads loss of statistical power. Okay? The first limitation is this one. In LSS14 paper, those response functions are estimated. In marketing, if we estimated some models, we select best one based on AIC or BIC. But in LSS14, the model comparison is limited among three models. They do not compare model fit between these three models and a threshold model and other models. So in their paper, as this morning, as Professor Brenner introduced, in their abstract, result of linear model and both result of threshold model is described. So that causes a really confusing impression. So this data is open for public, so I re-estimated these models and calculated AIC and BIC. And the BIC is, I think the BIC is the most strict criterion to select better fit and simpler model. The smaller BIC is a better model. Among estimated model, as you can see, this one, linear model, is the best one. So BIC for these are threshold model. Apparently, the number BIC is larger for this threshold model. So it is really clear for me that among estimated model, the linear model is the best one. Okay. The second one is aggregation of individual level data. In marketing, if individual level data is available, we apply logit or hazard model that's utilized full information of individual level data. But in LSSS, airborne survivor data, continuous variables such as dose and ages are categorized and tabulated, and the Poisson regression is applied. Such kind of aggregation and tabulation cause loss of information and loss of statistical power. Okay? Unfortunately, individual level data of airborne survivor is not released. So I looked for individual level data, and I found DOE released many nuclear worker data. Okay, so I reanalyzed pooled analysis data that's pooled Hanford and Oak Ridge and Rocky Flats data. Gilbert et al. Applied traditional approach and failed to detect effect of radiation. These are coefficients. All of them are insignificant. On the contrary, I applied binomial logit model for each cause, and multinomial logit, the people die one of cause. And I also applied hazard model for the same data. And as you can see, I obtained positive and significant coefficient. Okay? So this is an implication for low dose rate and radiation epidemiology. The first one, to reach correct conclusion, proper understanding of statistical modeling, such as model selection is necessary. And the second one is to detect low dose effect. Models that utilize individual level data are more efficient. Okay, thank you.
Well, thank you for a very interesting presentation. Time for a question or two on the last presentation here. Okay, if there are none, we're going to go into a more general discussion now, but before initiating it, I'm going to give Dale and Dan and Bruce an opportunity to offer just a brief statement before we open the floor to general questions. So, Bruce, you take the lead in terms of any general comments you want to offer at this point.
Okay. My final slide had kind of what I suggested as ideas for later, and my ideas for now are that, at least in the Techa River and MIAC studies, we see results at low dose rates that are roughly comparable with the instantaneous dose rates in the LSS, which implies to me that the DDREF is on the neighborhood of 1. It's not a whole lot different than that. The other thing that I thought was important is that the current situation in radiation dosimetry regulation is we use effective dose. And in effective dose, we add external dose and we add internal dose together. And what's interesting with both the Techa and the MIAC is that you can do that and you get essentially the same answers, which means that the entire construction of the ICRP models is pretty reasonable and possibly correct. So I'm damning with faint praise here. But I think that's
not far
important.
off.
They're not far off. So that's it.
With regard to the last presentation, in terms of individualized dose, have you done, the data is available, that could be done for those populations, is that correct?
We provide, Dale and Dan, 1,500 or 1,000, depending on the cohort, realizations of annual dose to 17 to 23 organs for all 30,000 MIAC workers and all 48,023 EURT plus Techa workers or Techa residents. So, and in that information, many of those people are based on their whole body counts, their residences, their individual basically life history.
So basically the data is there.
The data
for the
is
handoff.
available if you wanted to do a logit type of model.
Let's move on. And did you want to go, Dale? We go out of order, and you want to respond, extend that last comment?
Well, I'd like to say one thing about individual data and aggregation. For the analyses I just talked about, actually, the data were not aggregated. They were done as a person-year analysis, but disaggregated. So each individual has multiple records for small time periods, and that gives virtually the same results as in an aggregated analysis. And we're interested in rates. I think that is a reasonable and appropriate way to analyze the data, and we don't see any evidence of particular bias. And we've also been looking at that in the LSS. We started many years ago. And again, we don't see much evidence of bias, provided you use a broad array of dose categories, actually.
Yeah, very good. Do you want to offer any other general comments here while you have the microphone at hand?
Well, I would like to comment, I guess, on the dose uncertainty. I think for years, Owen Hoffman and others have been talking about the need for doing something about dose uncertainty, and I think Dan and his student have done a good job of coming up with methods that we are beginning to apply. Now, they do, in the past, people, when they've given us doses, even for these studies, they'll give us a dose and a number saying, oh, the GSD of this individual dose is this much, and that's not very useful for us in statistics. But these Monte Carlo systems, which are a pain to work with, but they do, by having this sample from the uncertainty distribution, you can actually begin to look at the impact of the dose uncertainty. And I think it's probably a little bit different than what people might have expected originally, but the pattern Dan showed of this sort of widening of the asymmetric widening of the confidence intervals is, I think, a sort of a realistic reappraisal of the kind of uncertainty we're seeing in the doses. So I think this is a real advance. It's coming out of these studies.
Well, thank you. Dan, do you want to offer some?
A few more things to Dale's comments about the uncertainty analysis. You know, it is asymmetric, and that's because the parameter that you're trying to get a confidence interval for affects the variance of the statistic that you're using. So that's the reason why so you get a bigger variance at a higher value of the dose parameter that you're interested in. For the other parameters in the model, the adjustment usually has only limited effect, and we can just and that this feature of having the variance dependent on the parameter that you're looking at doesn't apply, so it's a little bit simpler. But we do end up with corrected confidence intervals for all the parameters in the model, not just the parameter that you're interested in. So you could give you an example. You know, we saw that there was a widening of the confidence intervals for the males and females when we looked at plutonium dose in there. And now, before there was this widening of the confidence interval, there was a strongly statistically significant difference between the dose response for males and the dose response for females on this excess relative risk scale. And the question is, after the widening of the confidence limits, does this still apply? You know, is it still true that, or now do the confidence intervals overlap enough? And that's actually turns out to be a slightly harder question to answer with these adjustments because of the shared correlation. You can no longer think of the estimate of males as being kind of independent of the estimate from females, just because they're different people, because there's a shared uncertainty. But even that question, we do have some ability to test with this methodology. So I think it is a useful approach as long as you have some faith in the uncertainties or the Monte Carlo system that you've developed.
While Peter going to the microphone there, I'm going to open a little bit of a can of worms here, and that is the presentation that Dr. Hamaka gave. He noted that he did not have access to certain data in terms of the REF lifespan cohort. And I just say that I've had the opportunity to work with a particular pollutant. It's diesel engine exhaust. And I worked with a data set that had been assembled by NIOSH and NCI. Went through sort of the water torture, myself and my colleagues, to gain access to the data. We actually had to go to a central location and to use the data, submit a very detailed data analysis plan, but it was worthwhile. We used alternative, first replicated what others had done, and I would urge always when using those data sets, attempt to replicate first what has been reported by the others, and then proceed to do what I call extended analyses. And in my opinion, these do not necessarily mean one is better than the other, but I think the results of this multiple set of analyses then really strengthen our scientific understanding of what's there. Let's move on. I've got quite a lineup. Nick?
Yeah, very quickly. With regard to the dosimetry, then the human volunteer studies which we did at Harwell showed that women excrete twice as much plutonium as men for very good metabolic reasons associated with iron metabolism. That's the first thing. The other thing is I had access to a huge database which was being used in support of a drug application to the FDA on lanthanum. Yeah. And for that, I've got to be very careful what I say because they're refusing, the company's refusing to let me publish the data. But what I think it's fair to say is that if you look at the injection case, the injection data they had for the volunteers, the gut uptake they had for the volunteers, there's even data on hip biopsy for plutonium, for the bone content. When I went back and did an uncertainty analysis on the dosimetry, then I ended up with 95% confidence intervals of around about 2 orders of magnitude after an assumed 30 years of intake. So I think that though the central estimates seem to be quite good, once you start going down and actually fit in responses for distributions, probability distributions for the different components of the models, then you can end up with indications that you can be quite a long way out, even though the central estimates look pretty good.
Are there any comments, Bruce?
We don't have very many parameters that differ male and female. We do different body masses and things like that, but most of the biokinetic parameters are essentially the same.
Yeah, because you're using the ICFP model.
More or less. Yeah, we have our own lung model, but the rest of it is pretty much the same.
Let's move on. Dr. Mohan.
Yeah, Mohan. About the EURTC data, there was a publication in 1994 by Kostychenko et al., and that compared the cancer mortality rates in the cohort with the control population, and it showed significant reduction of cancers. But the follow-up study that was published recently, a few years back, there such a comparison was not done, but a linear LNT model fitting was done, and that showed, I guess, increased risk of cancer by the fit. I think you can take the same data, because when you divide it into so many doses, you have lots of error bars, large error bars, and you fit a linear model, then you can get excess related risk, but it doesn't mean it's a risk unless you compare it to a control population. So I want to know if you have such a data for comparison to control population of the risk in this cohort.
Comparisons to rates in Russia is extremely difficult. The quality of available population rates is very low. So I think one has to be very suspicious of that, and also how comparable this EURT rural population is to whatever those rates are based on is also problematic. I think being able to look at a dose response is a much more powerful method than making a simple comparison of rates in an exposed and an unexposed population. And so I think I would not have any faith in coming to a conclusion about dose response based on a SMR to a national rates or some other regional rates.
Just one more question.
It's a pretty naive approach.
The lung cancer rate that was shown, the dose response shape that was shown, that showed a hormetic reduction, but a linear model was fit to the data. The linear model will show the excess relative risk, but that relates to the high doses. At low doses, there was a reduction of cancer. So you cannot really say that what you calculated is for low doses.
You can also say that there's no evidence against linearity. If we fit a linear quadratic model, for example, which would allow risk to be less than 0 at low doses, you don't see any indication that that's better. In fact, those point estimates were just slightly below 0, but there were several that, and some are above 0 at low doses too. I mean, these are not very powerful tests.
This was a two-drink question, so
Okay.
I encourage you to continue that at the reception. Dr. Brooks.
When we were chasing fallout, one of the things that really impressed me was how much time influences dose. If you have an early release, there's a lot of short life stuff that can really drive your dose crazy. And so when you come in later and do your dose estimates, what do you do for that short life stuff? That's question number one. Question number two is we did a lot of stuff with plutonium under Roger there, where we'd inhale plutonium, it would go to the lung, and then it would go to the bone and the liver. So you'd have a dose to the lung, a dose to the bone, a dose to the liver, and then you guys combine that with a whole body dose, and then you use Grays. So I don't quite understand how you do that, because we know that the sensitivity of those organs is very different. So how do you add a dose to the thyroid, to a dose to the bone, and a dose to the liver, and a dose to the lung, and the whole body, and come up with Grays?
Go ahead.
I'll start with the first question, if the voice will allow me. Operations at MIAC were very complex and convoluted. They would dissolve fuel. They would extract as much plutonium as they could. They would store the materials in a tank until they ran out of fresh material to process. They would pump it back and process it again, and this went on with lots of mixing and
So
other
the short
things.
life stuff was gone, is what you're saying.
Things were not released immediately. The average age of stuff going into the Techa River is, I mean, Yuri Makarov says it's 6 months.
Oh, okay.
We did a very detailed analysis of the various processes that we have published, and there are different waste streams. Some of them go through various. I mean, some of them were just dumped on the ground and ended up leaching into the river. Others were released directly. We have a reasonably good handle on what was there because there were measurements made in the 1950s that we can compare to.
Okay. What about using Grays as opposed to Sieverts?
I give Grays to Dan and Dale, and they can do what they want with them.
Do you, either of you have any comments on that?
Generally don't add them together. We take a representative organ and use the dose to that organ as a surrogate for overall exposure. Now,
Yeah.
whether that's legitimate or not is, I mean, it's commonly done though, not just by us.
Ethel Gilbert did actually look at that, and she tried saying, well, what if all these plutonium things were multiplied by 20? You know, a quality factor.
That's what I was wondering. As you multiply by 20, that's what my old chromosome data used to tell me. But as we started to look at cancer, 20 ain't the number anymore. Down around 6 or 8. But that's just another thing. The other thing I worried a little bit, you did solid cancers except lung, liver, and bone in some of those. Now, if I'm inhaling plutonium, lung, liver, and bone are my target organs. So how come you excluded those?
That was for external dose. And
Well, that was for external.
that was external dose.
And so you said lung,
and-
liver, and bone, that might have plutonium
Yeah,
problems.
we exclude, and then I did give the lung cancer risk estimate independently, which is about the same as
What
the
about
other
bone?
solid.
I didn't hear anything about bone
I
cancer.
did, there's actually very few bone cancers. There appears to be sort of some indication of a bone effect, but the number of cases is very small.
Yeah, but a lot of the dose is from strontium in the bone.
Yes, yeah.
So you've got targets and you've got
There's no
bullets and targets.
but
Your
there's
targets and
no
bullets are
there's
different
no
places.
significant there's no evidence of a significant effect of other than plutonium for bones.
Well, I was
bone
thinking more Tika River. There's a lot of strontium in Tika River,
cases.
right? And
But we don't.
and you got a lot of the doses
Yeah, but there's-
strontium 90 dose to bone, right?
There's very few bone cancers.
I know. That's what
Yeah.
worries
Well, I
me.
think you go, no, it shouldn't worry you. You just need to go back and look at the miniature pig data that came from the study I was involved in here in 1960. And it's low. Actually, it turned out the bone cancer incidence from strontium 90 was substantially lower than what we anticipated when we designed the study, posed the hypothesis. Next.
Well, I have a question to Bruce. You mentioned that the DDREF would be in the neighborhood of 1 if you take the overall picture from the Russian studies. If you remember what I gave this morning on the results of the meta-analysis of task group 91 of ICRP, indeed we found also for Techa River that there is not much difference between the risk estimates compared to the matched lifespan study data, but for MAYAC it was a factor of 2 or 3 difference, and I think it was similar numbers Dan I think gave recently. Could you comment on that, please?
I'm just a dosimetrist. Well, most of my comments are based on the Techa because I've been doing the Techa for 25 years, and I've only been the MAYAC guy for about 6.
I made the comment that the MAYAC, those risk estimates do seem to be lower than Techa, and they also seem to be lower than the LSS. I mean, whether that's significant or not, it's a hard thing to say, but there are definitely differences there.
Next question.
My name is Olaf Christensen, and one of the observations I found interesting was also that the Techna River effects were similar to the lifespan study, and I would have expected them to be lower based on a biological response. So my question to you is, can we infer from that if there is a threshold for a hormetic response, it is at a lower dose rate than what was experienced for the people along the Techna River?
Dan,
yeah. Well, I mean, yeah. If you assume a low enough I think then you could get something that was in line with this, with the observation. I think.
But these are already pretty low dose rates.
Mm-hmm. Yeah, that's right. That for Techa River, the dose rates are so low that if you believed in a hormetic effect, then you would say there should be no effect at all.
Okay, let's move on. Randy.
Yeah, Randy Girdle. My question is a lot easier than that. It's an informational question. You had some beautiful radiation exposure cohorts that you presented this afternoon, and I'm just wondering, do you have DNA from these people, or can you get these samples so that you could look, for example, on potentially the effects of radiation on the epigenomes in these large databases? These are very unique cohorts, and it would be nice to be able to correlate what you're seeing with biological endpoints.
Dale, I can address that. Yeah, Scott.
Ariel, talk about the tissue repository.
The tissue repository for MAYAC would be a very important resource for that, and that is available. And Barry can talk about that in more detail.
Yeah, that's a great question. Actually, I regret that I didn't have sufficient time to discuss the MAYAC worker tissue repository, but it does include DNA samples, and we have family triads, cases where the father was exposed as a MAYAC worker, the mother was exposed, and in cases where both parents were exposed, plus the offspring.
So is there a standard process by which someone could get in contact with you?
Absolutely.
Yeah?
Come see me afterwards and I'll connect you.
Thanks.
So probably maybe to you, yeah. I think what is the situation for the biological dosimetry in Russian studies, and do they have chromosome and ESL and these be done or not? Because the reason why I ask is in the case of airborne survivors, DSO2 and chromosome aberration translocation frequency plotted gives you very wide scattering of the chromosome aberration data. Then you just plot this chromosome aberration data and ESR dose, it goes very nicely. So these two biological dosimetry seems to be merging, but the real DSO2 dose has so much human error because the information was collected in 57, and just listening and relying on the people's memory, so where you are at the time of bomb. And they may say, well, something like that. So there are many human errors, but biological dosimetry can supplement this kind of thing. So you have also difficulties in like biokinetics model or whatever, but that can be easily be supplemented by biological dosimetry, except that ESR doesn't pick up alpha, but gamma component can be picked up, I think.
Well, thank you for your questions. You've covered a lot of material, and I have answers for you. I don't know how much time we have to go into it.
Give them a short answer, and then you continue.
It would be great if you could pull up my presentation again, and we'll go to the tissue repository. That will help answer a lot of questions quickly. But yes, we have looked, actually, is David Brenner here? So David was, with his Russian counterpart, Tamara Azizova, actually led a study on radiation biomarkers in MIAC workers. And they actually proved their principle, which is to develop using peripheral blood lymphocytes, they were able to develop a calibrated dosimetry system using intra-arm chromosomal aberrations. And it showed the difference between alpha and gamma radiation. Does that kind of summarize it, David? Yeah. So you can talk to David, and actually these are all published studies. If you go to the program website, all of the list of all the publications are there, but one of the key reasons for having this biorepository is so that molecular epidemiological investigations can in fact be studied. So if you could go to the previous slide. Okay, so basically I told you it was unique in Russia. It preserves all this material. You have the gamma as well as plutonium exposures over a wide range of doses. And so right here, the contents facilitate molecular epi studies designed to assess the relationship between disease and radiation exposure. And that includes over 315,000 specimens from over 9,600 registrants. I don't know where the bottom's cut off, but anyhow, it includes samples from MIAC workers as well as Ozyorsk residents who were not occupationally exposed to radiation. Next slide, please.
It's not cut off on the other side.
Okay, next slide. Next slide, please. Okay, so I will walk over so I can see everything. So I was saying that the repository has 4 major components to it. The first is the autopsy tissue bank, which consists of archived autopsy tissues from over 1,000 individuals who died between 1951 and through the current time in 2008. The second component is the surgical biopsy tissue bank, which consists of surgical and biopsy tissue samples for both malignant and benign tumors, different sites through the body, from 974 individuals. The repository of blood and its components, and this addresses your question, suspensions of leukocytes, lymphocytes, immortalized B lymphocytes, erythrocytes, plasma serum, and extracted DNA from over 8,000 individuals. And then the fourth component is a bank of other tissues and includes buccal epithelial cells, those are cells lining the mouth, bone marrow, lymphoid tissue, cells from sputum from over 1,700 individuals. Does that help respond to your question, sir? Yes? Okay. Come see me if you have additional questions afterwards. Thank you.
Thank you very, very much for that. Next.
Rod Adams from Atomic Insights. One question I had that piqued my interest. You mentioned that there was very low bone cancer and this is an area where strontium-90 was a isotope of interest and a big contributor. Having read a lot of the fear literature produced by people like Gofflin and Tamplin, strontium-90 was one of their biggest isotopes of concern. Did you find, are there other cancers that are related to strontium-90, the bone-seeking strontium-90?
Let me just offer by a general, yes, strontium-90, cesium-137, iodine-131 on a short term were very important fallout radionuclides. Hanford, when I was here as a student intern and later I had responsibility for a major study we did on daily ingestion of strontium-90 and the development of cancer, bone cancer, and neoplasia. It was interesting. The initial study was 1, 5, and 25 microcuries per day of intake to be continued over a lifetime. I was an eager young scientist. I didn't see anything. Well, what do? You increase the exposure level. So I added additional animals. As it turned out in retrospect, what we saw in those cases was a higher incidence of hematopoietic tissue, dyscrasias, and neoplasia at the highest level. But at the end result of that study, I think the bone cancer incidence was relatively low. But there are numerous other studies done on strontium-90. Miriam Finkel at Argonne National Laboratory did studies with literally thousands of mice and looked at the pathogenesis of disease. The Utah study was one originally created with dogs to look at radium and plutonium. It basically was to try to understand what was going on there. And the concern for strontium-90, it was added. And then later, a study at the University of California, Davis, was done with daily intakes of strontium-90, periodic injections of radium-226. So that data is all available, all published. But I do find remarkable that in the miniature pig study, we did not see a very high incidence relative to substantial exposures to bone over long periods of time. So that's the data, and I'll just have to go from there. Let's go to the next question here, Dr. Seith.
Scott Miller, University of Utah. I've been involved with the Utah dog studies for my entire career, and I'm hoarse just like these gentlemen because I was with them in Russia Saturday. So we've been involved with the MIAC studies for 20 years. But I wanted to comment, just a couple of comments. Bone cancers keep coming up. Yes, there are not very many bone cancers in the Russian cohort. But we learned from the doggy studies that bone cancers have a unique profile. They have unique locations where they occur. And 12, 15 years ago, we published some papers looking at the locations of where these plutonium tumors occur. And sure enough, just like the dogs, the MIAC tumors occur in sites that have some very certain characteristics in the human, which would be indicative that these are potentially plutonium tumors. Little plug for the tissue repository. We've done some neutron induction with these tissues and worked with Sergey here with the USTR, done comparisons, and it's an incredible resource, particularly to be able to do these comparisons. We've done neutron induction, and I know they're doing some autoradiography, advanced autoradiography techniques. One last little teaser. We have some emerging data. It's not published, so I won't tell you the punchline, but we're seeing some unique pathologies with liver cancers in the MIAC workers. I won't tell you what those are, but they're reminiscent of the Thoratrast studies. And so we're working on that. We're also plugging that in. We're trying to get some DNA genomic data on that, and that's pretty exciting. That's coming out of Georgetown University. So just some plugs.
Well, thank you for that update. Let's take these last two.
Mark Miller, I'll be quick. I just keep thinking of the thread that keeps running through we're wrestling with how to deal with the LNT, and the LNT kind of governs our prior thinking to this. And it reminds me of Brant Ulsh wrote some papers in the Health Physics Journal about we've got it wrong. The null hypothesis is backwards. We're supposed to be proving that there is an effect, and in fact, we're doing it just the opposite. We assume there's a linear effect. In fact, there's not. But I'll close this by saying something my father, a farmer, nice pithy statement, says, what we're trying to do is about as hard as trying to put socks on a chicken.
Yes.
I'm Nancy Kerner, and I have a question for Bruce. I think you said that they released about 25-30% more iodine at MIAC than maybe Hanford. And I know when we looked at the Hanford historical dose reconstructions, there was no indication of congenital hypothyroidism, but with the extra iodine, is that on your forecast of things to look at?
Right now, there's not an active epidemiology study of the children of Ozyorsk, which is where we would really want to look, although Nina Kochernikova has wanted to do it for 30 years. There are signs of other thyroid diseases in the cohort of people in the city because they lived much closer to the release sites than Hanford residents did, and all the milk came from collective farms, and we know where the collective farms were, and they were primarily downwind.
Thank you.
Also, we looked ago at the children born in Ozyorsk in 1952 and 53, and children who were born in the same years who moved into Ozyorsk later and saw evidence of an increase in thyroid nodules. And there's some unpublished work where they looked at people, they identified all the thyroid cancer cases in Ozyorsk over the last 40 years. And there was some indication that people lived in a village of Tatish, which is in the closed territory, very close to Mayak, and where they could have their own cows, that they had increases in thyroid cancer. But there were no doses in that study. So,
Bruce, could you give a scale idea in terms of the location of these residents, location of the farms, to the facilities at Mayak?
The town of Ozyorsk is within visible sight of the stacks. It's about 8 kilometers, I believe. The town of Metlino, which is the first one downstream, is 6 kilometers. Most of the milk-producing areas, there were some in the city, there were some at Metlino, and there were some more than 20 or 30 kilometers away downwind.
No, thank you for that insight. Well, I think we've had some very interesting discussion here. I'd like to close with a few remarks going back to one of my slides this morning, and I related that radiation was the most extensively studied, ionizing radiation, the most extensively studied hazardous agent that I'm familiar with. I was really full-time in the world of radiation the early part of my career. Then I kind of segued into work on other energy technologies. And then I got tired of arguing over the length of the T, the crossbar and the T in radiation, the size of the dot. And I decided to go into a field where there was a lot more uncertainty of those. We could actually do things to reduce the uncertainty and not just argue about these issues. I don't mean to give light in any way of the discussion we're having. It's very important. But I can tell you that I would re-emphasize, having been reintroduced to some of this data today, my statement this morning, I would put a big exclamation point at it, and I could point to any number of chemicals. One of my good friends has spent a substantial part of his career in terms of benzene. We go back to the pliofilm markers. I think about the crude estimates that were available in terms of looking at benzene exposure, those individuals. I can go down the list of chemicals, and I can tell you radiation knowledge is up here and these others down here. We argue about whether a material, a chemical, is a possible human carcinogen, a probable human carcinogen, or a human carcinogen. We don't even get into the discussion of what is the dose-response relationship. So we have a very, very rich data set, as I think has been emphasized, and I think one of our challenges going forward, quite frankly, is to see if we can expand the pool of scientists who are using those data and doing, as I said, attempting to replicate the original findings and then proceed to all alternative analyses. I think that's very, very important, and it will solidify our understanding, and we again will honor those individuals who, as Mr. Parker said, were individuals in terms of the unfortunate that are the individuals that we are studying and attempting to tease out some very modest carcinogenic effect in general. So with that, I'll close it and turn it over. Tony, are you introducing the next speaker?